Last term we looked at force. Force is external stuff. This term we're looking at stress. Stress is internal stuff. And you could think of stress as a measure of how hard those atoms and molecules are being pulled apart or pushed together when you apply those external forces. And as we think about these atomic connections between these atoms, we realize that when we apply tension, the thing always gets longer, and then we let go of the force and it springs back. And when we apply compression, it always gets shorter, and then we remove the load and it springs back. So applying a force and causing stress always causes a change in length. You might remember from a math class or a science class that we use this triangle, the Greek letter delta, this is a capital delta, to stand for change. And you might notice that the Greek letter delta is where we get our letter D. This is a capital D, delta, capital D, and the lowercase delta in Greek looks like our lowercase d that kind of got squished. So in our math class or our science class, we use capital delta to stand for change, any kind of change in temperature, change in whatever. In engineering and strength of materials, we use the lowercase delta to stand for change in length. And this lowercase delta stands for deformation. Deformation means change in length. This is a mnemonic device. Mnemonic means memory. This is a memory device. D for delta, delta means change, helps me remember that deformation is represented with a delta. So deformation is a change in length, and that happens anytime you apply tension and stretch a body, or you apply compression and you shorten a body. It always happens. And in this picture of a rubber sheet getting stretched, you can see here's the original length of the sheet of rubber, and here's the deformation, here's the change in length as it got a little bit longer. You could figure out the deformation by doing the new length, call that L prime. So that apostrophe there, we say that prime. So the new length, L prime, minus the original length, L, is the amount of deformation. Well, that's great, but oftentimes we like to express those as a percentage. So just how stretchy is this sheet of rubber anyway? A real stretchy sheet of rubber would have a different ratio between deformation and length than would a sheet of rubber that's not very stretchy. So we call that proportion strain. We represent strain with another Greek letter. This is a lowercase epsilon. Looks a little bit like an E. So epsilon. You don't need to remember that. Strain is change in length divided by original length. So the amount of deformation per length, that is the strain. And a number of things could cause strain. It could be tensile stress, making it longer. It could be compressive stress, making it shorter. It could be a change in temperature, causing it to expand or contract. So here's that formula for strain. Strain is deformation over length. And by length, we mean original length. So deformation over original length That gives us strain. What units is strain in? Turns out no units, and here's why. We've got one length divided by another length. So for example, let's say we have a bar here. It's originally 10 inches long. Then we pull on the bar and it gets an inch longer. The deformation, the change in length, is an inch. The original length was 10 inches. And yes, I know, L prime, the new length, is now 11 inches, but we're not thinking about that right now. We're just thinking about deformation divided by original length. That's the amount of strain. So 1 inch, deformation, divided by 10 inches, original length, the inches cancel out. And we are left with plain old 1/10. So the strain for this particular bar is simply 1/10, or 0.1. If you prefer, it is also acceptable to say 0.1 inch per inch, if that feels better. That's okay. But most people just write the plain number with no units. And strain, deformation over length, could be a result of something getting longer, like stretching out this steel bar and it lengthens, or it could be a result of something getting shorter, like putting a big heavy load on this concrete test cylinder and it gets shorter. So let's think about that concrete test cylinder. Its original length was 12 inches long. It shortened by 0.036 of an inch, 36 thousandths of an inch. So the strain is deformation over length. The strain is 0.036 inch divided by 12 inches, or 0.003, or 3 thousandths. Notice that this strain number is not positive or negative. It's just a number. I wrote it's always a positive number. If you prefer, you could also think of it as an absolute number, and you could put absolute bars on each side. It's just a number. We never use a negative sign with strain. It's just a number. It's just a ratio. Let's stop here, and then we'll come back and look at several examples of strain.